Okay, I feel that some more students should join, but I will not able to make them join because once I go into the screen mode, it's not possible for me to come back and make the students join. Okay, so yeah, so why the number of students are less? That means any answer? CR, are you here?
Yes, I'm here.
Yeah, why the
Uh,
students are less today?
no idea. So we are texting in the group. We are telling them to join, but no idea, sir.
Yeah, so why that means nothing is now. That means I am. That means otherwise I have to go and take the class physically, right? Right, and then if you don't attend the class, okay, your attendance will be barred and you will be stopped to give the exam in the 8th semester, which is not good, right? So I am extending my maximum support so that you can okay continue your work in the 8th semester, whatever internships and trainings you are doing. But if you don't join the class, I have to take it physically, because all of you know that I take the class at this point of time. It's already, I think, for the last 5 weeks I'm taking the class like this, 5 or 6 weeks. So the schedule is defined and everything is defined, right? So I will wait for 2 more minutes and start the class, because already we are delayed by 10 plus minutes in the class. It's not good. You are all final year students. 10 minutes is a valuable time for anyone, right? If at this point of time of your career, if you don't understand the value of 10 minutes, okay, right, it's very pity. Okay, so 10 minutes is a valuable time for any person. So if I say it's a 10, it should be on 10. This problem shouldn't be there. I'm telling you repeatedly, it's not only your technical skill, right? Your skill should be professional skill. Professional skills means technical skills and also some other skills. Timeliness is very essential to get success. Okay, so let me start. Okay, whatever number of students are there, right? So today I think if you have a class size of 33, right? What's your class size? 33 or 40?
36, sir.
36. So we have just crossed the 50%. Actually, it should be 70% ideal. Okay, to take a class, but okay, let's start with 60%. Okay, the 50% of the class, because I don't have much time. Okay, to go ahead. Okay, so let me try start the class. Okay, so who can summarize what we discussed in the previous class?
So, spatial filtering process, the smoothing with using low pass and the sharpening
Right,
process.
right, right. And did you check that I will I will pass a okay, pass a PPT for this, but did you check with the book also? Because this is what I discussed in the previous class is the third chapter of Gonzalez, digital image processing. Okay, please go through the third chapter of Gonzalez of digital image processing, what I have discussed in the previous class. Okay. What I will discuss today, that means I thought I will be discussing on frequency domain filtering on today, but I looked and I checked that I have missed one topic in the spatial domain. Okay, so that I need to finish today, and which is called geometrical transformations. Okay, somehow I missed it in my, that means in my lecture. So I think I should cover it. I should cover the geometrical transformation today's lecture, and then from the next class I will start the frequency domain. Okay, so let's try to understand. So geometrical transformation, what I will discuss today, is also considered under the spatial domain transformation. Okay, so it's also the spatial domain transformation, but geometrical transformation means, okay, this transformation changes the geometry of the image, or geometry of the objects in the image. Okay, so Okay, so unlike the spatial transformation what we discussed earlier, okay, where we had used the spatial kernel masks, right, and we did the convolution of the kernel masks on the the image data. Okay, here also the kernels will be there. Okay, the kernels will be called transformation matrices. Okay, and these transformation matrices means it will alter the geometry of the image or the objects within the image. So these are specialized transformations which are called the geometrical transformations. Okay, so let me go to this to my paint window to start this. Okay, so okay. uh, okay, so what I will discuss today is something called, let me sorry, let me increase the Mhm. Okay. This is a problem. If someone joins now, it's very difficult for me to make the accept of that. Okay, so uh, is my screen is visible to all of you? It's visible, right?
Yes, sir.
Okay, so geometric transformation. Okay, okay. So is my script is visible? That means what I have written in this, it's that means you can see it, right?
Yes, sir. Yes, sir. It is
Okay, fine,
visible.
fine. So okay, so geometric transformations means that it is obviously there are two things we need to remember. One is when we try to do geometric transformation, it's a spatial transformation of coordinates. Okay, number one, and it is a sort of intensity interpolation, means it will try to generate some more value. Okay, in some of the cases, not that everything is interpolation. Means what? Interpolation means it's a statistical technique by which you generate points between the data, new data points, okay, in the data, which actually obeys the same function. Okay, interpolation is defined on a function where you try to generate more data points of the function, okay, than what is given to you. Okay, just to make it more visibly better. Okay, here also Here also it is in some case it is the intensity interpolation, means some of the filling of the data will be happening here. Okay, interpolation, intensity interpolation, okay, that assigns values to the spatially transformed pixels. Okay, you can take a note of this if you want, or you can just go to the Gonzalez book. Okay, so what does it mean? It means that it is a spatial transformation. So it means that I will give an image and I will say that, hey, I will do a translation, I will do a rotation, I will do a shear of this particular image, which means that it will generate a new image, which is also a transform spatial information of the suppose we give fxy, it will generate gxy, a transformed image. And in this transformed image, you might have to generate some extra points, okay, to make this okay, because when we will go for the geometrical transformation, like fine, like when we go the magnification, or okay, or what do we do, it's called the scaling operation. Okay, scaling operation, you have to generate some more points, you have to increase the scale of the image, scale of your data, which means that you have to generate some more points. Okay, so those are the things which we will be doing. Okay, now the basic transformations. Okay, okay, if you go to the basic transformations, I'm okay, oh sorry, there's let me go to the new stuff. Okay, okay, so okay, let me start from okay, so the basic transformations. Okay, so one thing you can just try to suppose an example. I'm just giving an example. It is not that we will do it in the same way, but just to get into the next part of this discussion, let's try to come with a very simple example. Okay, suppose I write a equation x dash y dash equals to t xy. Okay, and this can be expanded as t11, t12, t21, t22. So who can interpret this equation, what I am actually doing? Okay, first I wrote x dash y dash equals to t of xy, and this t of xy is expanded into t11, t12, t21, t22 as the coefficient of the matrix T and xy. So what this equation is doing? So what this equation is doing? Who can answer? If we expand, what is x dash now? Right? And what is y dash now? So is it okay? Is it okay?
Yes, sir.
So what this mean? What this mean?
Sir, does it mean that we are representing the values of x dash and y dash in using the components of t11 and t12?
First of
That
all, we
means
have
it
to
will.
decide that what are these x dash y dash and what are these x and y. Who can
Yes.
answer this question? What
So
are
can you
these
please
x, y,
repeat?
and x dash y dash? So xy are the pixel coordinates. So this is the difference between a normal spatial transformation and geometrical transformation. Try to understand that that here, that means I think I've given in the first discussion that here we are transforming the coordinates, not the intensity value, which means that x, y are the coordinates of the input image, and x dash y dash are the coordinates of the output image. Okay, so what does it mean? It means that the new coordinate, that means for each xy in my input image, there will be an x dash y dash in the output image defined by the transformation relation, which means that the same xy coordinate will move to a different x dash y dash in my new image, okay, which has gone through a geometrical transformation, and to which x dash and to which y dash will be defined by the this t. This t is an example of a translational matrix. This t is an example of a translational matrix. So there will be a translation which are defined by the coefficients t11 and t12, okay, coupling with the initial x coordinate and the input x coordinate and the input y coordinate, and will generate a particular, okay, will generate x dash in the new image. So the same pixel value xy in the input image will be translated to a different x dash y dash in the new image, and that is called a geometrical transformation. Okay, why? Suppose take it's a translation. What translation means? Translation, anyone can give an example of translation of an image? First of all, figuratively, let's try to explain this figuratively at first. Okay, so what a translation means? Can anyone say what a translation means in an image?
Sir, like shifting the image along the x-axis or y-axis.
Very good. So suppose this is my image boundary, and this is an object. Okay, now this is your input image, this is output image. So in the output image, the object is here. So what happened is that this was xy of the object, and it changed to x dash y dash. This was another xy of the object, this has changed to x dash y dash. This was another change, this another change, and all the intermediate points of the object have got shifted by some value. So this is the translation which has happened in the object. Okay, from this is the input image. Okay, this is the input, and this is the output. So what means that all the xy's have got a shift. So the the intensity doesn't changes. What we have given in the what we have done in the previous examples of spatial transformation, that we actually apply a kernel and we try to change the center pixel with the neighborhood information. Either we are doing mean, or we are doing max, or we are doing average, or we are doing a particular type of filter which multiplies -1 to all the neighbors, and maybe +4 to the center pixel and tries to do something. Okay, but here the coordinates itself gets transformed. Okay, so the same information but in a different coordinate value, and that is if it is a translation, it will be only a shift across x, only a shift across y, or a shift across both x and y. Okay, if the object only moves across x, then all the y's will be, that means all the y coefficients will be 0. Okay, right? Only it will be shift across x. Okay, if it is shift across y, the coefficients across x will be 0. But if it is shift across both x and y, which is a sort of diagonal movement, then both x and y will be changing. Okay, so am I clear to all? What is this geometrical, how the geometrical transformation is different from the spatial transformations what we did in the previous discussion, though both comes under the spatial transformation. Both comes from spatial transformation because we are just trying to operate on the pixels, but either pixel coordinates or pixel intensities. If it is pixel coordinates, it's a geometrical transformation. If it's pixel intensity, these are the normal spatial transformations by different masks, kernel masks. Okay, am I clear to all of you? Fundamentally, what? Okay, fundamental concept. Okay, fundamental thought process of the discussion. Are all of you are clear? Any questions? Anyone of you?
Yes, sir. Sir, I have a question.
Yeah.
Sir, what could be the possible use cases of this transformation of images? I mean, transformation in the sense of the linear translation or something, translation along the x-axis or y-axis or both. What could be the possible use cases?
Can you repeat once again? What? Can you repeat once again? Yeah, please. Yeah.
Sir, what could be the possible use cases of this
Oh, lot
translation
of
of
things. Image editing. Any image editing software you do, right?
yes?
That means I am just yeah. That means any image editing software you do, you can create animation, right? All your animations, what you do, okay? All your animations, what you do is basically these geometrical transformations, right? An object jumps, how it jumps. Okay, it is doing a random translation in every frame, right?
Okay, sir. So basically, we have nowadays we have seen so many softwares which are
Right.
able to move the image and make a video from it. So it's basically implement use case of this translation or the
Yeah,
transformation.
yeah. I mean, if you see,
Okay, sir.
that means if you want to move an object in an image, right? What operation you are doing? Though using a tool you are doing, there might be that means you are doing it in a cursor. But what is the computation being done with the cursor job? Computation being done behind the cursor job is that you define the translation coefficients. Okay, you just take a cursor from here and move the object, select the object. Okay, you select the object and do change it, right, and to push it somewhere there, right? So what it means that by changing the cursor and by picking the initial selection and then pressing the cursor where you want to push, okay, right, at the back end the translational coefficients are estimated, right, and the image is regenerated. Okay, that's all. Okay, so these are transformations which are required for various type of image editing operations, and also to compare the two images. Okay, many of the times you have, that means you have to find out that suppose you have a tumor, right? You have a, that means you have a CT scan taken 3 months ago, and you are actually taking the taking the tumor 3 months 3 months after. Okay, most probably the tumor has enlarged, or if medicine has applied, it has been shrinked. Okay, so now how to estimate that, what are the things? So that is called the scaling transformation. So the scale, so either it has reduced or it has increased, right? So all this, to comparing the two images, the objects in the two images. And also there is a technique called image registration. Okay, image registration is a technique where, okay, where the objects from multiple views or multiple modalities, the same object, are captured to multiple views or multiple modalities, but to the actual user a single information is presented. Okay, for example, if you are taking a CT scan of your brain. Okay, CT scan or MRI, so that is for brain MRI is better. Okay, because brain has a lot of water, fluid sacs. Okay, a lot of there are soft tissues are there. So for soft tissues, basically MRI is better. Okay, for hard tissues, CTs are better. Okay, but let's say that if I take an MRI of the brain, what it will give? MRI of the brain will give the structural information. So you can find out a lesion, which is a patch, which is something which can be a sort of tuberculosis or a tumor, whatever is the case. Okay. Okay, so the doctor will first do an MRI and try to find that, hey, whether there's an abnormal patch developed in your brain. Okay, now if the abnormal patch is developed in your brain, okay, then the next consideration is that whether it is active. Okay, a patch is active means whether it is growing phase. If it is on the growing phase, then I think immediate action is required. Okay, you don't have much time. Because soon it will enlarge, it will create a lot of disruptions. Okay, if it is not increasing, then you have, might be you have to still operate, but you have some more time because it is not in the growing phase, so you can actually take a precautionary measure, or if you see that it doesn't stops any processes in the brain, the location where this patch is, it is not growing, right, and it doesn't hampers anything, you can still tell, you can go to a conservative treatment of the patient. Okay, but how do you know that okay, it is growing or not growing? So what the doctor suggests that go for a PET. Okay, PET is a sort of imaging, which is okay, where it's called functional imaging. Functional imaging means you can able to identify whether the cells are active, whether the cells are actually living cells there. Okay, so what they do, the thing is that they actually can screen the glucose absorption rate in that particular region. Okay, if the glucose absorption rate is high, okay, then that can be trapped in the PET by the radiation what that particular cells generate, and PET can absorb the radiation. PET scan can absorb the radiation and can tell that, hey, this is a functionally active region. So now the difficulty is that our that means if I am an image processing developer, a tool builder who has to show the doctor that, hey, this was your MRI and this is your PET, right? You cannot confirm that the orientation of the two machines when MRI was captured and PET was captured and the orientation of the patient were exactly same. You cannot do that. You cannot do that in the real life, right? Two different machines at two different instants of time, all oriented in the same axis. You can't do that. Okay. So okay, so they captured the images in different times in different orientations, but ultimately they registered the two images. Okay, so they use this geometrical transformation. They try to take one image as the base image, and another image they try to do a rotation or translation to match or overlap, okay, that image with this image, and try to find the combination of the two information. Okay, so I'm giving you some examples of these geometrical transformations. There are many more examples of geometrical transformations, right? And you will be very happy to know that this is a real case. So okay, so Dr. Oyun Chatterjee, who is now an assistant professor in IIT Kharagpur Computer Science, okay, he was our student in MCA. He did my project under me in 2000, I think 2000. He was MCA, I think 2006 to 2009, or might be 2005 to 2008. Okay, he was the first student who worked with me on geometrical transformation, okay, for the stereo images, right, for medical diagnosis. Right, he did an excellent project in MCA. And later on, he moved to MTech and completed PhD, and now he's he's a faculty of IIT Kharagpur. So that point of time, 2005, 2006 or 7, the registration. Recently also, one of our computer science PhD student who was supervised by me got a PhD from a computer science department of CU, Dr. Vishwajit Bishash. That means some of you might know him. Okay, he's a very senior student. He's an MTech student of our department, and then did PhD. So the entire PhD work was, that means the 70% of his PhD work was on registration. Okay, so registration is so important. Okay, so that's why geometrical transformation helps you. Okay, So clear? Any questions? Any questions?
No, sir.
Okay. So yeah, so let's move on from here. Okay. Just one second. Okay. So now let me go to the next part of this. Okay. So now as I shown you this particular transformation equation, what we are trying to focus here is that we are trying to focus the transformation equations, okay, which can support scaling, okay, translation, rotation, and shearing. These are the four geometrical transformations which we'll discuss, right? And though we can argue with me that, sir, all this transformation can be just of this dimension, that means your T was 2 cross 2, right? Okay, as you are transforming, so your basic equation is that your x dash y dash, your new pixel coordinates, will be resulting from a transformation of the old pixel coordinate xy, and this can be a 2 cross 2 dimension transformation matrix, because your x and y is a vector of dimension 2, and xy is also a vector of dimension 2. But unlikely, okay, we cannot keep this dimension of the transformation 2 cross 2 if we want to do all this transformation in a similar way. So all this transformation as a set are called affine transformations. Okay, this is a very important term, you need to note it. Okay, affine transformations. Okay, so these affine transformations are the transformations which is a scaling, translation, rotation, shearing, and the two, that means any movement of the object in a given image is a combination of all this. Okay, it might be that it's only translation, which means scaling, rotation, shearing, all are 0. But you can always define an object movement or a geometrical transformation of an image, okay, which consists of all fours together. Okay, so now to make all this uniform, it has been understood that a 2 cross 2 transformation will not work. Okay, so the beta transformation matrix for this is basically 3 cross 3. So the generalized affine transformation equation looks like this. Okay, this is the affine transformation matrix, and if we expand it, it will be something like this: A11, A12, A13, A21, A22, A23, and then 0, 0, 1, and this is x, y, and 1. So this change in dimension is being done just to make the operations all uniform. That means it's the same size of matrix, which will work for all the 4 transformations. And that's why this type of matrix is there. So the variable part of the matrix are A11, A12, A13, A21, A22, A23, and 0, 0, 0, 1 are the static components of the matrix. Whatever, so when you move the transformation, this A1, A11, A12, A13, A21, A22, A23, this will all change. Okay, others will all be same. Okay, right? And you only have to expand x dash y dash 2 or 3 component vector, which is the x dash y dash 1, and similarly xy is a 3 component vector, which is xy1. Okay, so any difficulty in understanding this particular equation from the preliminary equation, we have got to this equation to make everything uniform. Okay, and this is called affine transformation. And now I will go one by one to each of this transformation. Okay, Before that, any question, anyone of you on this understanding? Yes, no?
Understood, sir.
Very good. Well, okay. So let's try to go to the transformations one by one and finish the stuff quickly. Okay. So so the first one is obviously identity, doing nothing, but still we have to keep it. Any transformation equations will have an identity operation. Similarly here also. So the identity affine matrix is 1 0 0 0 1 0 0 0 1. Nothing happens. Nothing happens. So if you actually operate this, actually the new x dash will be same as x and the new y dash will be same as y. Okay, still we have identity just to make the set complete. Okay, now the second one, the second geometrical transformation what we try to discuss is called scaling. Okay, scaling is defined by this matrix. If you operate, what happens is that your new x dash is cxx and your new y dash is cyy. What does it mean? If cx and cy is greater than 1, what does it mean? If cx and cy is greater than 1, what does it mean? Anyone? Very good. Because this each xy, okay, that means the intensity values of each xy will now go to, suppose it was in 2 2, now it will go to 4 4. Okay, which was 4 4 will go to 8 8. So which means that you have that means you have actually done an enlargement of the image. Okay, right. The third one is called rotation. Now this rotation is always, you have to remember about the origin. What is the origin of an image? What is the origin of an image?
Sir, a pixel.
No, origin. Yeah, pixel is the distribution of the image. But what's the origin of the distribution? What is the 0 0 point of the distribution? The top leftmost point. Right? I've discussed in the previous class. This point. This point is the origin. 0 0 coordinate. Is it clear? And this
Yes, sir.
coordinate, the end coordinate is m minus 1, right? The last coordinate is m minus 1 and n minus 1. The last coordinate, right? And this is your m, and number of x pixels, number of pixels in the x direction, and this is n. Is it clear to all of you? What is the origin means of an image? Right? I think I've discussed this, right? In the previous
Yes, sir.
classes. Okay, now it's clear, right? So rotation about the origin means you have to take this, okay, take the theta from the origin. Okay, so let me rub this one. Let me rub this one. Okay, so the rotation across the origin means that the matrix is like this. Okay, cos theta minus sine theta 0. This is 0. Okay. Sine theta cos theta 0. Which means that if this is your origin, okay, this is your origin, you are rotating the image by an angle theta. Okay, so that means if suppose this is your object, and this is your this is some line you take from the origin. Now you try to make this theta, this is the theta, right, and try to shift it by theta. Okay, that means from your initial orientation from the origin, you are trying to shift it to theta. Okay, try to rotate it with theta. Okay, towards the, okay, that means this theta will be measured as an angle you rotate, okay, from your initial orientation with the origin. Okay, so you try to connect the origin with your object, right, and then try to see if you move theta, find theta. Normally it is in the in the anti-clockwise direction. Okay, that means in this direction, in this direction is normally taken the theta. Okay, so if you try to move it in this direction theta, okay, that means across the origin, what you need to do, you need to do this transformation, okay, for both x and y. Okay, and let me rub this again to tell what will be the values of x dash and y dash. So the new x dash will be x cos theta x cos theta minus y sine theta is the new x dash, and new y dash will be x sine theta plus y cos theta. Okay, so this is what is a rotation about the origin means. Clear? Okay, is it clear to all of you?
Sir, in the matrix, there is minus sine theta.
Minus sine theta, yeah.
Okay, sir.
Yeah, it's minus sine theta because you see it's minus sine theta. So what you are actually doing, you can just generate this by just assuming this here is x, y, and 1, and in this side we have x dash, y dash, and 1. So if you equate, you will get the same thing. X dash equal to cos theta x minus sine theta y plus 0. Okay, y dash equals to sine theta x plus cos theta y, okay, plus 0, because then 0 and 1 will come up. This is all. Okay, so this is what is rotation. You can just, that means I'm not giving this equation, I'm only giving the matrix, and I'm giving the x dash and y dash solution, which automatically tells you that how the matrix will operate. Actually, the matrix equation is our old equation. Okay, as I said, x dash y dash 1 equals to a x y 1, right? And this A is the matrix what I am telling for each of the transformations. Okay, let me take one more page. So okay, so now we go to the translation, which is the easiest one, I think. So the matrix is 1 0 tx 0 1 dy and 0 0 1. This will generate x dash as it will be x plus dx and y dash as y plus dy. I think you can get it, right? You just consider that you have an x dash y dash 1 in the left, and you have an equal to, and this gets multiplied with x, y, and 1. So if you do this, you will see that the new x dash is x plus tx, new y dash is y plus ty. Okay, is it clear? So you have you are moving an object which has a shift of tx in the x direction and ty in the y direction. So it means that if the object was here, okay, now you have shifted it. Say this is your ty, and say this is your tx. Okay, so the object will come here. Is it clear to all of you? Tx and ty shift.
Yes, sir.
Okay, okay, okay. So this is the tx and ty shift. Generically, both should be there, but if you are only moving across x, ty will be 0. If you are only moving across y, your tx will be 0. Okay, good. Now I go to the last two. It's called the shear. Shear means something where you actually what I can say. Shear means something where you actually okay, that means you actually hold one point and stretch another side. Okay, so this shear is vertical, which means that if initially the example what is given by Gonzalez, suppose they have shown an object as t. This is your normal t. Okay, now if you do a shear vertical, what will have this vertical, it will be sheared, so it will be like this. So the t will be vertically sheared. Okay, it will be just pulled down. Okay, so this is called vertical shear, and for the vertical shear, the matrix is 1 sx 0 0 1 0 and 0 0 1, which means that all your x's are only scaled. Okay, all your x's are only scaled. So x dash equals to x plus sxy. So all your x's are scaled by y dash remains same. Okay, this is shear vertical, and if we try to do shear horizontal, this is I think the 6th one, right? You correct me if I'm wrong. Shear horizontal, then this means that, oh, my object was initially like this, again the same object. Okay, and shear horizontal means you will have a stretch in the horizontal. So what it means is that it will have same like this. It is a shear horizontal. Okay, so it moves horizontal, it gets a shear. So shear horizontal matrix is actually better to don't give y or this, better to give as given by Gonzalez, better to give this as sh and the previous one as sv. Okay, don't give sx and sy. I'm changing it here. Okay, try to remember that in the previous case also you have to just give sv. Okay, so I'm given a sh, which is a shear horizontal. Okay, so here x dash remains the same. Okay, but y dash changes. So these are the geometrical transformations which actually governs all the orientation changes of an object in an image. Okay, whatever orientation changes of the object you have in the image, it will be done by a combination or by their by only one of the transformations or a combination of transformations in your image. And this is very helpful in the application, as I said, image registration, when the images of the same objects are taken across time or across different modalities or across different views, you have to make all the objects, all the views in the same geometrical plane. So some have to be, so you take one as a baseline image, and others you need to map with the baseline image. You try to find out what are the rotational, translational, or scaling parameters we need to estimate. Okay, what it means that you suppose suppose this is an image. Okay, this is an object. Okay, right, and you have also captured the image of an object, but the camera position was tilting. Okay, so your object was this. Okay, this was taken by camera 1 and this was taken by camera 2. Now your responsibility is to make both the images in the same plane. So what you can do, you can take this as a baseline, right, and estimate the parameters what has been done here, and you can just do a rotation or whatever is required to make this image oriented like this. And this is the process called image registration. Okay, this may be the one application of this, as I discussed. Second application may be change detection. So suppose instead of a non what I can say a non-living object, this is a living object. Okay, right, and one point of time you have found this and one point of time you have found this, right? And you try to estimate what the change has happened over time. So you need to find the parameters by which you can actually, from here you can go here, and then you can try to find out what are the things have happened in this particular environment or the living object or a cell or a tumor. Okay, what are the more things have happened so that resulted this. So these are very good examples of why we require geometry transformation. Apart from image editing, third may be your image editing, animation, all these things. Okay, you require this animation, right? You require to that means you require to translate your objects, you require to shear your objects, you require to scale your objects. Okay, that means in your scene at different points of time. Okay, so that you can create those type of, that means those type of scenes which are attractive to your viewers. Okay, is it clear to all of you? So this was remaining in the spatial transformation, and it's good that I have covered it. Okay, so this is again Gonsalves chapter 2. This is Gonsalves chapter 2, though we have moved to Gonsalves chapter 3. Right? So I'm closing the class here. Okay, I'm closing the class here. You will get everything from the Gonsalves book, and right. And if you have further questions, let me know. Does anyone have any doubts or questions on the discussions today? Please go ahead. Yeah. No, if you apply both shear, it might be. Yeah, if you apply both shear, it might be. It will stretch then both in the x and y, which will be a sort of parallelogram. Yeah. Okay. Yeah, you can do a lot of transformation of the objects, right? right, using these techniques, geometrical transformation. So both the transformations are important. Spatial transformations which work with intensity values, and geometrical transformation which works with coordinate values. Okay, both are important. You have to know that what has happened. So if you are trying to detect a change in the information of the image, you have to look into whether the image is the intensity domain information or coordinate domain information. If it is coordinate domain, then you have to find what are the transformation values, what has been done to change this image. Okay. So any further questions, any one of you? Fine. So thank you all. We will meet again on the next Monday. And right, and that means I will try to push up some notes, but again I'm telling that it's straight away going to Gonzalez's book. Okay, it is available PDF format in the net. You can also have a physical book, right? I will always suggest to go to the physical books. It will be better for your eyes, right, and for your concentration, because in digital domain we cannot concentrate for a longer time. Okay, so thank you all. Okay, meet you in the next Monday, right? Any questions you have for what are the topics I have prepared, you are free to put in the Google Classroom. I will answer them on my time. Okay, thank you all. Okay, right, and if you want to meet me today at the university, I will be there today from 1 to 4 p.m. at the university, and again on Friday 1 to 4 p.m. at the university. Okay, anybody has anything to do with me, right? That means you want to, okay, come to my office physically. Okay, today 1 to 4 and again Friday 1 to 4. Okay, thank you.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you.
Thank you, sir.